Today we are going to discuss to find a very important parameter of lattice, and this is actually interplanar spacing. When you say interplanar spacing, that means the minimum distance or the shortest distance, or you can say the perpendicular distance between two parallel planes of a lattice. Actually, this discussion is limited only to the orthogonal lattices. So the result which we will obtain for the interplanar spacing, that is the perpendicular separation between two parallel planes of a lattice, that will be valid in case of orthogonal lattices only. And for calculating the interplanar separation or distance or spacing between two parallel crystal planes, let us consider a set of parallel planes which is defined by the Miller indices HKL. You know, HKL represents a set of parallel planes. And this point O shown in this figure is taken at a lattice point of such a plane. And then we consider another adjacent plane. It means a crystal plane which is also defined by this indices, that is Miller indices, just after this plane. And that plane actually is drawn, and that plane cuts the crystal axis, or you can say the crystallographic axis ABC, at points A, B and C shown in this figure. So ABC is a crystal plane which is parallel to the plane on which the origin O is lying. Okay. Actually, these crystallographic axes ABC, or you can say OX, OY and OZ, are taken mutually perpendicular to one another. That's why I have told you earlier that our result will be valid only in case of the orthogonal lattices. Okay, because we are considering that the crystallographic axes A, B and C, or OX, OY, OZ are parallel to one another. Okay. This second plane, which is parallel to the previous one, intersects the crystallographic axis, as I have told you, at point A, B and C, and the intercept of this plane ABC on the crystallographic axis are what? You can see the figure. Since the Miller indices are HKL and the lattice constants are ABC, so the intercept of the plane ABC on this crystallographic axis, you can see the figure, are OA equal to A by H, OB equal to B by K, B by K, and OC will be equal to C by L. Okay. Now let us draw a perpendicular ON. You can see the figure. This line ON is a perpendicular drawn on the crystal plane ABC from the origin O, which is lying at the another parallel plane. So this the length of this perpendicular ON, which I have marked by this D, which is equal to ON, this is actually the interplanar spacing. This is the shortest distance or the perpendicular distance between the two parallel planes indicated by the indices HKL. Okay. And our aim is to find the length of this perpendicular, that is, our aim is to find this D. Okay. And for this we consider that the angle made by this ON with the crystal axis OX, O and OZ are what? You can see the figure. We assume that the angle between ON and the first crystallographic axis OX or A is NOA. NOA. And we assume that this is equal to alpha, as you can see the figure. Again the angle NOB, that is angle between the perpendicular and the second crystallographic axis OY or B, that is equal to beta. We consider it. And angle between ON and OC, that is NOC, we assume that this is equal to gamma. Okay. So in this condition, you can say that the direction cosines of the vector ON vector, which is equal to vector D, or you can write it D times n hat, where n hat is a unit vector in the direction of this perpendicular. So the direction cosines of this vector D, you can say will be what? That will be cos alpha, cos beta and cos gamma. Okay. Since this vector D makes angle alpha, beta and gamma with x-axis, y-axis and z-axis, which are crystallographic axes. And so the direction cosines of this vector D are cos alpha, cos beta and cos gamma. From the geometry of the figure, we can easily find what will be this cos alpha, cos beta and cos gamma. And after knowing the values of these direction cosines, using a very important property of direction cosine, we can easily find what will be the length D. Now see, I have make all those calculations. What I have explained, I have mentioned it here. You can see I have written, consider a set of parallel planes with indices HKL. Take origin on the lattice point of one such plane and draw crystallographic axes A, B and C, or OX, OY and OZ. Now consider another similar plane adjacent to this plane. Since the second plane also has Miller indices HKL, so the lengths of the intercepts on ABC axis or OX, OY, OZ axis are what? OA equal to A by H, as I have explained the figure, OB equal to B by K and OC equal to C by L. Okay. And as I have told you, we draw a perpendicular ON and length of this perpendicular is equal to D, which is called perpendicular separation or between the adjacent plane, or interplaning, a spacing or distance or separation. Okay. Now, as I have told you that angle NOA is alpha, NOB is beta and NOC is gamma. For calculation, I have made here three figures for showing the actual situation, because in the original figure the triangles are not appearing as right angle triangle, but all these triangles shown in this figure are actually right angle triangle. As a perpendicular has been drawn from O and which falls at point N, so angle at N is equal to 90 degree. Okay. And this angle NOA, as you can see this first figure, NOA we have assumed it is equal to alpha. Okay. And OA, which is intercept of the plane ABC at the first crystallographic axis, the length of this OA is equal to A by H and length of the perpendicular ON is equal to D. So in this first figure you can see I have marked that ON is equal to D and OA is equal to A by H. From this figure, you can find the first direction cosine of the vector D, which is cos alpha. That will be equal to what? That will be ON divided by OA. But you can see ON is equal to D and OA is A by H. So cos alpha will be D divided by A by H. Or you may write it as this is H times D by A. Okay. And so from here, we can easily say that this D is equal to A by H times cos alpha. Okay. Now we have assumed that angle NOB, this angle is beta, and ON again is equal to D, and OB is the intercept on the second crystallographic axis, and that is equal to B by K. So from this second figure, you can find the value of the second direction cosine, that is cos beta, and that cos beta will be what? This will be ON divided by OB. But ON is again D and OB is B by K. So cos beta is equal to D divided by B by K. And equivalently, you may write it. This is KD divided by B. Okay. And so D can be written as B by K into cos beta. Similarly, you can see this third figure, as you have assumed that angle NOC is equal to gamma, ON is equal to D, and OC is equal to C by L. This is actually the intercept of the plane ABC on the third crystallographic axis. And so cos gamma will be equal to ON divided by OC, but ON is D and OC is C by L. So cos gamma is D by C over L, and that can be written as LD divided by C, and so D will be C by L times cos gamma. Okay. So in this way, in this equation, we have defined the three direction cosines cos alpha, cos beta, and cos gamma of the vector D, which I have written here, you can see. Now, one of the very important property of direction cosines is what? This is the sum of the squares of the three direction cosines is equal to 1. So you can write that cos square alpha plus cos square beta plus cos square gamma, that equal to 1. Now we will substitute the value of cos alpha, cos beta, and cos gamma from equation 1 in this equation 2. And you can see cos alpha is equal to this much. This is H times D by A, cos beta is KD by B, and cos gamma is LD by C. So squaring these and adding, what we will get? You can see D square will be a common factor, and the remaining terms will be H square over A square plus K square over B square plus L square over C square, and that will be equal to 1. And so that you can see D will be equal to 1 over a square root of H square by A square plus K square by B square plus L square by C square. This is actually the expression for the interplanar spacing, that is the minimum distance between the two parallel planes of a crystal. But as we have assumed that the crystallographic axes A, B, and C are mutually perpendicular, so it is obvious that this is not a general result. This expression for the interplanar spacing will hold only in case of the orthogonal lattices, that is in the lattices where the crystallographic axes are mutually perpendicular. For example, you can see that in case of cubic crystal you can use this formula. In case of orthorhombic lattice you can use this formula. In case of tetragonal lattices you can use this formula. because all these lattices are orthogonal. Okay. Actually, in this case, you can see there are two crystal planes. Let us say this is one crystal plane and this is another crystal plane, and both are parallel to one another, and this is the interplanar separation between them, and both crystal planes are characterized by the Miller indices, sorry, HKL, HKL, okay, HKL. So you can see that this formula is the interplanar separation between two crystal planes defined by the Miller indices HKL, or you can say that this is separation between the two crystal planes HKL. So in this expression, this D is also denoted by DHKL. Actually, this subscript indicates that this is interplanar separation of the planes defined by the Miller indices HKL. Okay. Now let us see some of the special cases. If you are talking about a cubic system, you know that in case of cubic lattice or simple cubic lattice, you know A, B and C are equal. So when we will substitute A equal to B and that equal to C in this general result, what will be our expression? This A square in the denominator will be taken as a common factor as it is inside the square root, so that will be A, and that will be now in the numerator after multiplication. So in case of cubic system, you can see that this D will be equal to A over a square root of H square plus K square plus L square. This is the simplified form in case of cubic system. Similarly, in case of tetragonal system, you have learnt in the Bravest lattice that in this case A is equal to B, but that is not equal to C. So in this case, when you will use A equal to B in that general result, D will be like this. This will be H square plus K square over A square plus L square over C square whole to the power minus half. Okay. Now we will see the different planes of a simple cubic lattice. If you are talking about the crystal planes of a simple cubic lattice, then DHKL, this is the general formula for cubic system. This is A divided by this much. Okay. Now if you talk about the crystal planes defined by the Miller indices 1, 0, 0. So if you consider two crystal planes 1, 0, 0, the distance between such a two crystal planes, that will be denoted by D1, 0, 0, and that will be what? That will be A divided by 1 square plus 0 square plus 0 square whole to the power half, because here in this case H is equal to 1 but K and L are 0. So this is simply equal to A. It means in a cubic system, the separation between the two crystal planes marked by 1, 0, 0, that will be equal to A. But if you consider the another planes of the cubic system defined by or designated by the Miller indices 1, 1, 0, then separation between such two planes will be denoted by the symbol D1, 1, 0. And that will be equal to what? That will be A divided by a square root of 1 square plus 1 square plus 0 square. So that will be A by root 2. Okay. And if we consider the plane 1, 1, 1 in the cubic system, then the separation between two such planes will be denoted by D1, 1, 1, and that will be a divided by root over 1 square plus 1 square plus 1 square. That is simply a by root 3. So you can see that the separation between the two planes 1 0 0, the separation between the two parallel planes 1 1 0, and the separation between the two parallel planes 1 1 1 in a cubic system are not same. So if your aim is to find the ratio of the separation between these two planes, what will be the ratio? The ratio of D100, D110 and D111, you can see this will be A is to A by root 2 is to A by root 3. A will cancel out, and so the ratio will be 1 is to 1 by root 2 is to 1 by root 3. So from here we can easily see that the planes 1 0 0 are more separated than the planes 1 1 0, and it is more separated than the planes 1 1 1. So the planes 1 1 1 are more closer to one another, and the planes 1 0 0 are more separated. Actually, this idea is very useful in discussing the crystal structure. So after knowing how we can find the expression for the crystal interplanar spacing or separation, this concept we will use in the determination of crystal structure. Okay, but as I have told you earlier that this formula which we have derived here is valid only in case of the orthogonal lattices. Actually, when we talk about non-orthogonal lattices, such an expression may not be obtained easily. One may need to find the unit vector n hat by some other method, or direction cosines by some other method. So this is the simplest situation, but this is very important, particularly for your examination purpose. Although in examination it is not mentioned that you have to find the crystal interplanar separation in case of orthogonal lattices, but whenever it is asked to you that find the expression for the interplanar separation or interplanar spacing, you have to write this answer. Okay, thank you very much.